We're on page 14 of Pre-Calculus Honors Notes. This is section 3.5, Growth and Decay. I'm going to try to work maybe one page at a time, but we may go 2 pages. We'll see. So these are just exponential equations, really. That's just the a and that's the b, and then it's raised to some power, just like any of the other exponential functions, except that the exponent represents time and a constant. So it's made up of different things. Okay, so let's look at what these things are. The size of the population at any time, and it might be bacteria or whatever, is A at T. And the original population is A sub 0, A naught, as some people call it. K is a constant, typically called K in all kind of applications. And it's determined by the rate of growth. If K is greater than 0, then the population is going to grow or increase over time, not negative, in other words. This is called the exponential law, or the law of uninhibited growth. If K is less than 0, then the population decreases or decays over time. And these graphs are typical of the exponential functions. The x-axis is the t variable, and this is the amount that we have at 0 time, and it will increase exponentially if K is greater than 0. If K is less than 0, the constant is less than 0, negative in other words. You have something, here's the A, the initial amount, and it will be decreasing as time increases. So it looks like the decay graph. So we're going to use a couple of different applications to show exponential growth and decay in action in real world situations. And the first one will be uninhibited growth and typically cell division. That's what we're talking about. We're going to use the same exact formula, except some of the notation will be slightly different. N sub 0 will be the initial number of cells. And this uninhibited growth of bacteria, living organisms, little things like that. K is greater than 0, so K is the growth rate of cells. And it'll be a positive constant. Okay, first example, bacterial growth. So a culture of bacteria obeys the law of uninhibited growth. If 300 bacteria are present initially, and there are 500 after 1 hour, how many will be present in the same culture after 4 hours? How long is it until there are 10,000 bacteria? So we've got a couple of different things that we're given. 300 is the beginning amount, so that'll be N sub 0 in this particular one. 500 is how many you have after when T is 1. So that gives us enough information to start finding a general formula for the growth rate, for the growth of these bacteria. And we need to find K. We need to find the constant K. So that's our first task. And that, again, is the growth rate, like interest rate in a compounding interest problem. We're going to use some information that they give us. We're going to use the point 300 when x is 0, when the growth is, when it's the beginning amount, when time is 0, and 500 when time is 1. So in that equation, so we're going to say 500, that is n at 1 equals 500, which is equal to 300 times, which is the initial amount of cells, times e to the k times time, which in this case is 1. Okay, so we divide both sides by 300, get 5/3 equals e to the k, because we have k times 1. And then we're going to take the ln of both sides. And that's the constant. There's no need to calculate a value for that. You're just going to store it in the calculator at that amount. So we'll put in the ln of 5/3, and we're going to store it, use the little store button, as x, so that we'll have it when we need it. If you want to write it down, you could write down a rounded value, but you're not going to use a rounded value in your calculations. Okay, now we're going to start answering the questions they give us. They want to know how many will be present after 4 hours. So that's our second task. So now we're going to find the number after 4 hours. So we want to find n at 4. So that'll again equal 300 times e to the ln of 5/3, that's our constant, times 4. And when we calculate that on the calculator, we get 2,314.815, a rounded value bacteria. You can stop the video at any time that you need to do the calculations yourself if you want to. And then the next thing we're going to be doing is we're going to find the amount of time it takes to get 10,000 bacteria. So we're going to find T for 10,000 bacteria. And so that's the ending amount. So that's n at t. And again, we start at 300. E to the t times the ln of 5/3. Okay, we're going to divide both sides by 300, and we end up with, after reduced values, can take 1,000, t I'm going to pause this just a minute. And, okay, I'm not pausing anything, it looks like. E to the ln of anything, by the way, you know, is the anything. So this ends up being 300 times e to the t times the ln of 5/3, so it's just t 5/3 to the t power. Okay, because this would be the same as 300 times e to the ln of 5/3 to the t power. So that's what we're doing. 5/3 to the t power, 300 times e to the ln of that number gives us that. Okay, and then we can simplify this. So it's 100 over 3 is equal to 5/3 t, and of course to the t power rather, and we take the ln of both sides. And so t is equal to, when we bring it down, okay, so it equals the ln of 100 over 3 divided by the ln of 5/3. That's what t will be. And when we do that, we find that t is equal to 6.864 hours. That's our time after 10,000, till we have 10,000 little bacteria. Okay, and then population on page 15, we'll start in on that. These are pretty simple applications. Once you realize that they're just exponential functions, you're going to use a logarithm to help solve them. Remembering that the formula for these, for population, A of t, the amount of people at time, the population at time, A sub 0, the initial amount, times E to the K, T just to remind us. So the population of a Midwestern city follows the exponential law. If the population decreases from 800,000 to 600,000, from 1998 to 2000, what will be the population in the year 10,000? In 2010, sorry. So we're given some information. T equals 2 to find our constant from 1998 to 2000, and we're going to find K by using that information. So the ending amount is 600,000. Beginning amount was 800,000. And that's E times E to the 2, which is the time, the K, times the time, which is 2. K times 2, that doesn't look much like it. I divide both sides by 800,000. We get 0.75 is equal to E to the 2K. And again, we're going to typically always take the ln of both sides. And we get 2K on the right. And we get the ln of 0.75. And so K is equal to the ln of 0.75 divided by 2. Okay. So that's what the constant rate of increase will be. Will cause an exponential increase. And so they want to know, what is the population in 2010? We're going to use the same equation with our 800,000 beginning amounts, sorry. And in 2010, T will equal 12 years, because from 2010 to 1998, which is the original initial amount. So the population in 12 years will equal 800,000 times E to the 12 times that constant ln 0.75 divided by 2. After a while, you get to where you just put, you know what K is. Sometimes you just want to put E to the 12K. That's okay. We might do that later. All right, so then you calculate it. This is just a straight calculation, really. You put it in your calculator. And so we want to store this as X so that you get an exact value, or closer to a better approximation of the amount. And you end up, when you do the calculator, 142,382.813. Obviously, you can't have 0.813 people, but you do have approximately 142,382 people, whole people, no arms and legs left over. Another application, radioactive decay, follows the law of uninhibited decay. So it decays down to, it continues decaying, never stops. The amount A of radioactive material present at time t is given by the same model. K is less than 0. So A sub 0 will be the beginning amount. And K is the rate of decay. And we would expect a negative number, although we're going to just store things in the calculator again. All right, radioactive iodine is a byproduct of some types of nuclear reactors. Its half-life is 60 days. That means that after 60 days, the given amount of radioactive iodine will have decayed to half the original amount. I'll show you what that means in just a minute. Suppose a contained nuclear accident occurs and gives off an initial amount C of radioactive iodine. Part A. Write an equation for the amount of iodine present at any time t following that accident. And then how long will it take for it to decay to a level of 20% of the original amount. Okay, let's talk about what half-life is. You probably know more about this than I do, but half-life means that the ending amount is always half the beginning amount. So if you start with 100, you're going to end up with 50. If you start with 1,000, you'll end up with 500. So every time, and then you divide both sides by the 1,000, every time you're going to end up with 1/2. So let me show you. If you start out with A of t equals A sub 0 times e to the k times t, the amount every time is going to be A of t divided by A sub 0. And that's going to equal 1/2 every single time. So we can actually say that since A at t will equal that, over divided by the initial amount, we can just make the equation this way. 1/2 is equal to E to the kt. Okay, so when we divide both sides by the initial amount, we get 1/2 always, so that we don't have an initial amount anymore here. But it's basically the same formula we've been using that's up here. Okay, and we need to find a constant, find k, so that we can write the equation for part A. That's what we're going to do. So A of t is equal to ln of 1/2. You have 1/2 is equal to E. They tell you the half-life is 60 days. So that's the time at 60 days they've given you. So that's E to the 60 times the constant k. When we take the ln of both sides, we end up with 60k over here. And so k will equal the ln of 0.5 or half of 1/2 divided by 60. And again, you're going to put that into your calculator and store it as x. So the equation will be A at any time t, the initial amount, times E to the t times the ln of 0.5 over 60 That's the original, that's the initial, that's the equation. And then B. How long will it take for it to decay to a level of 20% of the original amount? Well, 20% is similar, acts the same way as 50% acted. So we want 0.2 will equal e to the t times the ln of 0.5 over 60. And now we can take the ln of both sides, get the ln of 0.2, and that will equal t times the ln equals the exponent times the ln of 0.5 over 60. E raised to the k's. Okay, and then we're going to divide both sides by the ln of 0.5 over 60. So we get, multiply both sides by 60, I guess. So 60 times the ln of 0.2 divided by the ln of 0.5. And that's equal to t. Okay, so now use your calculator, and you'll find that that's 139.316 days.